接下来进行今天的第一场专题演讲 BGP Security Threats and Challenges。让我们欢迎台湾网路资讯中心黄胜雄董事暨执行长为我们主持。The first keynote speech is BGP Security Threats and Challenges. The moderator is Dr. Kenny Huang, member of the board and CEO TWNIC. Dr. Huang, please.
Okay, right. Thank you. The next speaker I'm going to introduce is Geoff Huston, a chief scientist from APNIC, and he's going to introduce, as I mentioned, BGP security threat and challenge. As you know, the Facebook just happened yesterday or the day before yesterday. They just happened to have a BGP outage, and probably Geoff Huston also can share some of his view with us for the emerging event. Geoff, the mic is yours.
Thank you very much, and good morning, everyone. As I share my screen, let me apologise firstly for the Australian education system. I was taught languages other than English. They just happened to be not Chinese. It happened to be French and German, which for Australia is rather useless. So this speech will be in English, I'm sorry, because I'm not sure French or German would help. So, and I can't do Chinese. So hopefully you will see my screen, and let me just go to a full screen here, and hopefully you will see that. So I'll talk a little bit about Facebook in a second or two, but you know, I think there's a bigger question, and that is, it doesn't happen every day, but it keeps on happening. That we get these routing mishaps, and they happen all the time, and we don't seem to be able to stop it. This particular one was on the 13th of November in 2018. Nothing terribly special, apart from the fact that Google went down. Now, is Facebook going down worse than Google or not? I think they're both pretty bad. And we shouldn't be seeing this. How did the Google one happen? Oddly enough, it all started in Nigeria, where some small ISP in Lagos leaked a whole bunch of routes that normally belong to Google. And the world thought, and in fact, not all the world, but China Telecom thought, new information for Google. It's now relocated to Nigeria. Let's send all the traffic there. Oops. You know, and this just keeps on happening again and again and again. Why? Well, part of it is, this is what we built. Because we've been building for a long time systems that required people to construct the map, to actually work off tables. The entire telephone network of the 20th century wasn't dynamic. It was actually a bunch of tables that got filled in, and the system had no flexibility, no self-healing. We wanted something different for computer networks, and we built one. We built one that learned itself. No maps. No one's in control. Literally nobody is in control. And so this system is not only self-learning, but to the extent that it can, self-healing. That links can be cut, but connectivity will still survive. That's amazing. We'd never built something like that. And oddly enough, over the last 20 odd years, we've never built anything this big before. It's flexible, it's robust, it's scalable. It's amazing. We're about to approach another milestone in the V4 BGP space. We're kicking around 900,000 routing prefixes. And in the next few months, we're going to hit the big million. And I'm pretty sure nobody will notice, because it just scales. It just quietly gets bigger and bigger. And if we cast our mind all the way back to 1994 or 95, nobody ever thought that the internet would last this long. OSI was meant to save us or something. And no one ever thought it would get this big. There weren't that many mainframe computers. And of course, at that point, all of these devices, no one thought they were going to happen. So this is a world we never dreamt of. But oddly enough, this technology from 1993, BGP4, and in fact, the original BGP, 1989. We never thought it would scale for this long and this hard. But good as it is, it could be a whole lot better. Why? BGP is a rumor mill. I just tell you everything I know, and you believe me. And as long as we're all honest people, that's a perfectly fine system. But if one of us is a liar, everyone else believes me. Because no one can tell what's true and what's not. Now, if I lie in routing, I can cause your packets to go to different places without you even being aware. I can divert the traffic and have a look at it and then send it off to its destination. I can actually impersonate somebody like, your bank, your local infrastructure, your water supply system, your electricity grid. I can be someone I shouldn't be. Or very crudely, I can turn you off. I can divert all the traffic meant to go to Google and send it nowhere. Now, that's not what happened to Facebook, and we'll get to Facebook. But certainly with a solid routing attack, I can turn things off and so can you, because we trust each other. The problem is that we also trust the internet to work properly, because this is no longer about mere theft or criminality. So much of our lives are on the internet these days. Everything we do, our infrastructure, our water supply, our traffic systems, our flight control systems for aeroplanes, all of those bits and pieces completely rely on the internet. And these attacks can be massive. Facebook is not small. It affected billions of people. Is that massive enough? Or they can be highly targeted to just one city, just one location. Routing attacks go from the massive to the minute and everything in between. So the threat is astonishingly big. And sometimes the routing attack is actually not the end point. And a very good example was in April 2018, where criminals decided they wanted money. What a motivation, eh? Who would have thought? And they did a raid on an application, My Ether Wallet. And it was a multiple step raid. But what they actually did was they attacked the DNS and they took over a domain name for a small period of time to then make a certificate authority issue a fake certificate for which they knew the private key. The certificate authority should never issue the certificate because there was a routing attack going on. They didn't know they were being fooled because they didn't check BGP. Why should they? That then gave them enough of the credentials to actually mount the attack. It was all over in a small number of hours. It didn't take them long to set up. They didn't care what fingerprints they left afterwards because they got the money. So routing can sometimes get you into more insidious attacks. And now let's talk about Facebook and yesterday. This was a classic case, I think, of poor engineering inside Facebook. Because Facebook, bizarrely, took all of their DNS authoritative servers and put the authoritative information for Facebook.com behind one prefix. And then, one day, it was always going to happen, they managed to withdraw that prefix from the routing table. Now, they didn't withdraw Facebook itself, they just withdrew the name. Because once you withdraw that authoritative DNS server, no one could resolve Facebook.com, which is as good as it's not being there. but it was worse than that. Their entire internal command and control system used, you guessed it, Facebook.com. Even the automated door locks to their facilities to let employees in and out of the building was keyed against, you guessed it, Facebook.com. One prefix in the DNS and 3 billion people had a problem. And because Facebook was locked out of their digital infrastructure, locked out of their physical infrastructure, because they shot themselves in the foot over BGP, they couldn't fix it. And so, as usual, when catastrophes happen, the first few, hopefully minutes, but sometimes hours, is spent trying to figure out what's going wrong, trying to figure out where the problem is, what should we do about this, what is going on. But once you've sort of worked that out, and don't forget, they couldn't use any of their internal tools because Facebook.com was dead, you then move on to the second phase. How do you fix it? Without having access to your routers, access to your buildings, access to your digital infrastructure. I actually think it's amazing they fixed it in 6 hours, because they really did manage to engineer criticality right in the middle of their network against the DNS. And so what I'm not talking about today, but you should be aware of, is that the threat environment is as much about naming infrastructure as it is about addressing and routing. And just having a good routing story doesn't stop a disaster like Facebook's. Interestingly, having a good naming story gives you different problems in addressing. You need both. And, Facebook certainly, hopefully, will never, ever, ever run its own authoritative DNS from inside its own address space anymore. They should have at least outsourced some of it to a third party. But oh no, Facebook moves fast and breaks things. To quote Mark Zuckerberg, sometimes it breaks itself. Oops. Moving right on. So what do we do about this larger problem of the weakness in the routing system? Now, a lot of the time, we actually design better applications, but improving the host system, improving iOS or Android, or improving the app won't make this better. You can't. Because routing attacks actually don't make my system misbehave inside the system. They rely on every last piece of software working perfectly. The disaster is out there in the internet. My packets are going to the wrong place. Nothing wrong with me. Something is wrong with where my packets are going. Now, good application design can help. Everything should be encrypted these days. Everything. Even DNS queries really should be encrypted. And we should all be using TLS, Transport Layer Security, because TLS gives you two protections. One, even if someone diverts the traffic to look at it, if it's encrypted, it won't help. What you're seeing is just scrambled bits. So TLS gives you end-to-end encryption. That's good. But TLS does something else, which is also really good. Whoever impersonates me successfully needs my private key, needs to get information from me that I should never, ever, ever divulge to anyone. And so if you don't have my private key, no matter what you do to routing, you can't impersonate me. And for me, I mean your bank, your trusted service, google.com or facebook.com or anyone else. And so TLS gives you that level of protection as well. So in some ways, the worst of the problems, deceiving users, is much harder if everyone uses TLS. But I can still turn you off. I can still disrupt you. And quite frankly, the end host systems can't patch that up. Even the DNS can't make that better. You just can't. The only way to fix this is actually inside the routing system itself. And so, as good as we are with TLS and improving applications, we need to look at the routing system. So, can we detect the difference between the truth and a lie? Can we make our self-learning system, which is just a bunch of routers chattering, can we figure out whether some of that chatter is genuine and some of it's been falsified information? That's hard, but that's what we want to do. That's really where we want to be. This is not a new problem. It actually dates back to the 1950s when we first started thinking about automated networking with computers. Some really good work by Paul Barron at the Rand Institute in the early 60s. Now, the issue is that the way this works is that every single speaker gathers information, processes it, and sends it to its neighbors. No one understands the entirety of the system. There's no one in control. You can't get above and look down. There's no higher information. We don't know what's truth because no one is outside this system. BGP, like most routing protocols, suffers from tunnel vision. Here are two views of downtown Philadelphia. They both came from Google, oddly enough. One of them is from Google Street Views, and that's what BGP sees. It looks down a path, but what it can't see is the map on the right. Because that map on the right comes from virtually moving outside the street, above it, and looking down. But there's no outside of the internet. You can't look down. And so BGP has to construct the map on the right here, the city map, from a whole series of pictures of the left, a whole series of views down streets, and somehow hope that the view that it is constructing corresponds to the correct map. That's about the most graphic way I can illustrate that these protocols are very limited in the information they get, but they're very ambitious as to what they're trying to do as a result. Construct the map on the right from a whole bunch of pictures on the left. And that's a tough question. So what we want to do is not only construct that map, but make it the right map. And we don't know who's being naughty, who's being bad. So we want to avoid propagating reachability when the address that I'm being told, I can reach network 10. No, you can't. That's not a real address. That's just used for private addressing. That's not a good address. I can reach this network that hasn't been allocated yet and it's not in anyone's registry. Well, no, I don't want to know about that address because it's not real. It's bogus. I'm connected to this network over there. No, you're not. Don't tell me that. It's a lie. And the other thing is when I really am connected to someone and I tell you, no, I'm not. Oddly enough, that's a lie too. And so we want to avoid those kinds of lies in the way addressing and reachability is said. Now, this is a big problem space because in some ways, even the information we're working with has its problems. We'd like to understand where every IP address comes from. Who owns it? Where is it? We don't know. We really don't know. Not for every address. We know it for a lot of them. We don't know every address. And even then, we actually don't know which networks have the authority, the permission to originate a route in the routing system for that address. We don't know. And even then, we still don't know the map of the internet, that interdomain topology. And even then, we don't understand the policies that apply. I'm a customer. I really shouldn't announce the routes I learn from one transit provider to another. That's a no-no. That's a policy no-no. Sure, I'm connected to both providers, but don't leak routes. That's a disaster. So in some ways, those policy constraints are as important as the other ones. Now, that means we have no model of truth. Who has the legitimate authority to announce a prefix? What's the topology of the internet? What are the policies? Oh, what's the best route? Not just any old route, the fastest. Oh, that's really a problem. We can't solve that. That is something that is just too big a problem. We can solve a weaker problem. Can we actually look at changes to what we're currently doing to resist attempts to deceive us? So instead of worrying about the bigger picture, let's just worry about the flow of information. Can we detect lies from the truth in routing updates? Interesting. Because in some ways, we're kind of getting there. You know, if we had the map of the internet, this would be easy. But what about a stable set of routes that should be visible everywhere? Would that help? And interestingly, it does. Now, there are various ways of looking at this picture, and one of them is to apply artificial intelligence, anomaly detectors. And there are a few out there, and I don't know, they kind of got two problems. One, they really don't know what's good and what's bad. It's just all pattern matching. But secondly, and perhaps a bigger problem, is that it only happens after the disaster. It's like a smoke alarm. Smoke alarms don't stop fires. They just tell you when there is a fire. It's an alarm after the event, not before the event. It doesn't stop it. So what we want is something that says, you're telling me something. Before I believe you, do I like what I see? Is what you're telling me okay or not? That's what we want. So we've been working on this problem, and we've been working for, I'm tempted to say 20 years, but let me say conservatively, it is a good 15 years, and there's been a lot of work. Now, why do we know about truth in a digital system? Digital signatures are brilliant. Digital signatures is the base technology, because a digital signature is something that if someone tries to tamper with the data, it's immediately obvious. But a digital signature also involves me, my key, if it's my signature. So no one else can represent me, and I can't unsay it. I can't deny it. And so on top of these digital signatures, we designed a public key infrastructure that binds these key pairs used in digital signatures into ownership of address prefixes and autonomous system numbers. Now I'm getting to somewhere interesting, because if we put out tools that allow folk to make digital authorizations, signed attestations, then as network operators, you could then filter that information and see if there's a digital signature attached to that information and accept it as the truth if the signature matches and deny it if it doesn't. Now, we hoped that in building this, and this is a huge body of work in just those 5 bullet points, and a lot of money, a huge body of work, but we hoped that network operators like you would say, that's really cool, let's adopt it. And it was that last thing that actually is not good. We just hoped that you'd all see the advantage of this cool technology and just turn it on. But economics says no. Because when you're doing something for everybody and everyone has to do their bit, economics says, you know, the problem with common benefit is that it very quickly becomes no one's individual problem. So no one feels responsible. And so just identifying that everyone would benefit doesn't mean that every network reckons I should do something to make it happen for everybody. A lot of our world in economics is based on the idea of self-interest, whereas common interest is much harder. And what that means is that you need to be incredibly patient. We've been playing with V6 for 25 years. When I mean incredibly patient, I mean 25 years or possibly more. Adoption is likely to be slow and not necessarily going to complete anytime soon. So how are we doing? Well, we'll look at some metrics that talk about how well we're doing with adopting this technology. The first stat is the number of origination attestations, digitally signed, provable. Over 2 years, it's grown from nothing to 280,000 rowers. Don't forget, we only have 1 million routes, so it's roughly 1/4. Jaw-droppingly fast. Great work, world. We're moving quickly. What about routing systems? How much of the routing space, 900,000 routes, is actually covered by a valid rower? We're getting to 1/3. We're getting to 300,000. Great work. And again, this is over only a few years. So that part, brilliant. Even V6. Someone did something really cool in June and it jumped by a clear sort of 50,000. So we're up to 50% in V6. Again, fantastic work. Edging 500,000 routes in 6. How many folk are playing? Now, don't forget, there are around 70,000 networks out there in the routing table, different ASs. A lot less, about 3,000 folk actually regularly check into RPKI and gather the data every few minutes. So in some ways, that number is not so good. But again, it's risen from 1,000 in, less than 2 years. So while it's still a low number, it's certainly growing a lot. What I don't understand about that figure is why is the number higher in weekdays than weekends? Do some of you turn off your computers when you go home in the weekend? Routing doesn't stop, okay? So don't turn them off. When you set up an automated system to do this, just let it rip. 7/24, no weekends, sorry. But the last measure, the really last measure, the one that counts. What proportion of users in the world won't get duped by false routes? 2 years ago, it was around 15%. Few variations at the end of December in 2020. That was probably my fault. Where are we today? 15%. And that is both unexpected and unacceptable and kind of sad. That all of this work, and some of it is great work, but not enough people have actually taken that last step. When RPKI says that's a bad route, drop it. Don't let your users go to it. But that's not happening. Only a few edge networks have actually been doing dropping. We seem to be doing all the hard work in generating the prefixes and credentials and then going, you want to take that last step? No. Don't want to make it real. Oh, come on. Who's doing it? This is a map of the world. The greener, the better. Greenland, yay! Denmark, yay! Australia, sort of. Is that Uzbekistan? Sort of. Syria. There are some odd countries in all of this. Sweden, yes. Finland, no. Let's look a little bit closer to home. Now green is 35% of users. Japan, Taiwan, Mongolia, and sort of South Korea. China, North Korea, not so. You see, even then, even with this, it's still not enough. Because oddly enough, I can still mount an attack by faking the AS path. So the last piece of this puzzle is to actually protect the AS path. We're working on it. It's being developed in the IETF, partial deployment models. It's certainly looking promising, but we're still at the tests and trials. And at the pace we're moving, there's a few more years yet. Other activity, you may well have heard of activity from ISOC with manners. Look, their hearts are in the right place, but trying to convince everyone it's a code of conduct is like convincing everyone that they should do source address filtering for spoofed source addresses. And we've been telling everyone about BCP 38 for 25 years now. So while I applaud ISOC for the effort, it's just so hard to get folk to listen, and I'm not sure they've really uncovered a magic way of doing it. BGPsec, a number of folk are talking about it. They're talking about it in Europe at this point in time, dead on arrival. It's just too heavyweight. No one's going to run this. It's just not going to work. And I've seen a whole bunch of research papers about blockchain. It's very fashionable, but completely deluded, because that's not the problem. It's not the ledger and the registry system that's the issue. That's not the problem. So the bits that blockchain can do differently, doesn't work here. It's integration into BGP that's the issue. So in the last few minutes here, let me just ask you a few questions. What can you do? What are you going to do? Well, you really should use the RPKI to sign your address holdings. You really should generate ROAs. How are we doing in Taiwan? Well, of all the routes advertised out of Taiwan in both V4 and V6, 70% of those routes are now covered with a ROA. Fantastic. Big green tick, elephant stamp, gold star, you got it. This looks great. How are you going with filtering? How are you going with saying, that's a bad route, I won't send my users there because the route origination validation failed? Pathetic. There was a small period where it was sort of around 55%, and then somehow it didn't. So someone did something in September, and then they decided it was too much. Silly people. Who's doing it in Taiwan? HiNet, AS3462, but oddly enough, only for about a third of its users. Yeah? What are you doing? EMOME, EMOME, AS17421, better, 53%, and that's still a big network. And Far East Telecommunications, even better, AS9674, love your work. And then we move into the folk where very hard to love the work. The rest of these folk just aren't. I'm sorry, they're just not. And so in some ways, the task is take this seriously. You've done through all the ROA generation, you've done all the signing, you've done all the rest of that work. Go and filter, because that's a big fail. Could do better. Don't forget, over at APNIC, we are here to help. And we're here, if you have questions, if you want to know, find case studies and so on, to actually give you confidence that this will work. We are here to help you. So that's my time. Thank you very much. If you have any questions, feel free to ask them now, or feel free to ask me later. I'm always online somewhere or other, or send me email. Thank you, and over to you, Kenny. Thank you.
Okay, thank you, Geoff. Thank you for introduce very comprehensive detail about what happened in Facebook. And I just remember what you say. It doesn't happen every day, but it just keep happening. And so we still struggle to figure out what's the best way we can do. As an operator or as an institution, what can we do from our side? And you probably propose a very good recommendation. For example, like a route validation. That's what we try to promote. All the operators try to validate their route and try to filter all the invalid routes. I think that's some way we can do. I'm probably starting from here. Okay, anyway, thank you very much.